So I'm going to talk about maybe one of the killer apps for vision and language, which is helping blind people. And this is, the motivation is very similar to the motivation Meg Mitchell gave this morning. I don't know if she's here, I think not. Okay, so here's a stock photo image of a blind guy, and he has a cane and a walking dog. Seeing eye dog, I think, is the preferred term. And you can imagine he's maybe got a camera in his glasses, or he could take his phone out and he wants to ask about the environment. So this seems like a pretty worthy goal, and it raises lots of interesting technical challenges, and also has some overlap with robotics. So one thing, so there's sort of two versions of this problem, right? One is when you're embodied in the world and you're walking around and you want to do real-time vision. And I'll come to that later. The other setting is a little easier. Maybe you're just living in the virtual world, in social media land, dealing with internet images or personal photographs, and you might want to describe these images, which might be out of context. So this is just a screen grab I took from something Facebook launched recently, which they call automatic alt text. And if you look closely, what it's doing is something very primitive. It's just image tagging, right? So this one on the right, they say the image may contain two people smiling, sunglasses, sky, outdoor, and water. So to sighted people, this isn't very useful, but to visually impaired people, this is actually kind of a big deal. But it's clear we could do better, right? It would be nicer if we could generate captions. So you have an image like this, rather than just listing the objects that are present, you might want to generate a sentence. Okay, so this is a well-studied problem. The problem is with captions is that they're hard to evaluate. So this seems like a good caption for that image, but you could say that caption also applies to this image. So it's not very, it's not unambiguous. Similarly here, right, that caption applies to all of these. So you might say, okay, let's make a more detailed description of that image on the left, but that also applies to this image. So it's very difficult to come up with something that uniquely describes the image, and therefore it's really hard to evaluate whether the caption is useful or not. And this is a well-known problem. So in this work, we took a slightly different approach. We built on this concept of referring expressions that Alex Berg mentioned this morning, and which actually Meg Mitchell has worked on. So this is a well-known thing in the linguistics community. And the idea is as follows. So you have a two-player game. So I'm the speaker, I'm trying to communicate something to someone. And a lot of computer vision and language work ignores the fact that language is about communication between two or more people. So you need to think about intent and what the purpose of language is. So here I'm trying to communicate to you that I'm referring to this specific part of the image, so the guy on the right. So I have to generate a sentence or a caption to describe that region, and then the listener receives that message and has to decode it and figure out what I was referring to. And the nice thing about this problem is that you can measure accuracy by just like mean squared error in pixel space. Like you can see where did they click on, and if they clicked on the object I had in mind, then I've described the region correctly. So now we have a nice objective measure, and it takes into account sort of the reason that people communicate. So specifically, there's two parts of this problem. The speaker task, you're given a region of interest, and you have to generate a description of that region, and you can use local features and global context features. And then the listener has to receive the string plus the image, and then decide which part of the image that string is referring to. And we simplify the problem a little bit by having a finite set of region proposals that we choose between. So this is building on work that was mentioned this morning from the UNC group, the Refer It game. In their work, they focused, I think, they only focused on one of these two problems. I forget which one it was. I think it was the generation task. Anyway, we're doing both, and we're going to do it end-to-end with, of course, deep learning. So we're going to have one model that will do both, and it's important, as I'll show, to treat these problems at the same time. Okay, so a baseline approach to this would be someone gives you a region, and then you just throw a standard image captioning machine at it. Okay, so this is what we did. So there's a variety of LSTM variants you can use and a variety of CNN variants you can use. We are using both features from the whole image and features from the region and concatenating them, and then we also include location information, like relative location of the region within the image. and throw them in as features, and we just train this to maximize the likelihood of the observed sentence given the region. Okay, so that's sort of a straightforward adaptation of previous work. Now what about the listener? Well, like I said earlier, what we're going to do is we're going to have a small number of region proposals, like 100, and we need to discriminate which one the speaker is referring to. So we can pick the region with the highest probability given the sentence in the image, and then by Bayes' rule it's just given by this. So if the prior is uniform, we can just ask which region has the highest likelihood of generating the sentence, and that's the one we decode to. So this is the max likelihood decoder. So we're using the same model for the speaker and the listener. Okay, so that seems straightforward. But if you think about it a little bit more, there's a fundamental problem with this basic approach, and that is that the model, it has no incentive to generate unambiguous descriptions. So if I give it a region, say this green box here, it might say a smiling girl, which perfectly describes that region. But of course it ignores the fact that there's 2 smiling girls in this image, so it's not going to do a good job at making an unambiguous description. So we want the speaker model to pay attention to the fact that there's ambiguity and to modulate what it generates as a result. Okay, so this is actually being studied by other people. So there's a nice paper from Percy Liang's group where they took a game theoretic view of this problem. So basically there's a lot of symbols here, but the idea basically is that the speaker and listener want to collaborate, and the expected utility of a spoken sentence in the listener is obtained by, let's see if we can parse all these sentences. I'm not going to try to parse them all now, but the bottom line is basically you're going to maximize the utility if you pick a set of words which assign higher probability to the true region compared to the other regions, right? And that's going to be mutually beneficial to both parties. So you can formulate that either as like a max margin type thing or as a discriminative, as a softmax loss, where you've got a set of regions and you want to pick the one that's most likely out of all of the regions instead of just looking at them individually. So more precisely, the setup is the following. We looked at 2 training objectives in the paper. So this is, in the speech literature, this is called MMI training, maximum mutual information. It's just maximizing the posterior of the truth instead of the likelihood, right? And the reason that matters is that you're going to look at the true region, but you're going to compare it to all of the other regions. So you're only going to have a high score if this sentence is discriminative between the chosen region and the other ones. And then you can relax the softmax and do a max margin thing instead, if you want. And these 2 approaches give very similar results. The max margin is maybe slightly ahead, but I think that's in the noise. The intuition is the same in both cases. So now we have our 2 models. Let's see, we need to apply this to some data. So we extended the COCO dataset, as a lot of people do, and we collected data very similar to the refer game. So we have 2 phases. So we pick a region of interest, which is coming from the ground truth COCO, and we only focus on images where there's at least 2 instances of the same class, so there's some ambiguity. If there's an image with just one person, you could say the person, and it would be uninteresting. So we require that there's at least 2, and I think at most 4, and we have some other criteria, like it has to be a certain size. So if it's a very small thing, it's going to be very hard to describe. So after applying these filters, we have 26,000 images that survive that test. And then we ask mechanical Turkers to describe the chosen region. And then we send that chosen region to a listener, which is another Turker, and they have to click on the region that they think is being described. And if they decode it correctly, then the pair both get rewarded. So it's very similar to the refer game setup. Here's some examples of what the data looks like. So we click on this region, and then someone says, this is the black and yellow backpack sitting on top of a suitcase. Or another worker says, this is the yellow and black backpack sitting on top of a blue suitcase. So you can see that they're pretty nice sentences. And we have, it's a relatively large data set which is publicly available. Now, by contrast, the data set that was mentioned this morning from UNC, so there's the original paper, the original data in the refer game paper, and then they've extended it to use a similar methodology on COCO. Maybe because of the nature of their gamification, the sentences they get are very short, whereas the ones we get are nice and flowery. They're over-specified, as Meg Mitchell would say. And we didn't tell them to do that, but there's more adjectives than you technically need here. We do experiments on both data sets. But the gref, the Google ref referring expression data set, the languages are maybe a bit more interesting. Okay, so let's see how it does. So we got our data. It's a standard supervised learning problem. We turn the crank, fit it with SGD, blah, blah, blah. Let's see how it works. Okay, so here's an image. I borrowed the blah, blah, blah from Jitendra. It's a nice verbal tick he has. So here's an image, and we'll say a sentence: a dark brown horse with a white stripe wearing a black studded harness, and it picks out red box out of, I think we're showing the top 4 candidates. I forget I think we use about 50 region proposals in the experiments, but we don't show them all because it's too cluttered. So that's a pretty good decoding. Certainly of the one shown, it's the best match. But what's really cool is that you can change the sentence just a little. A white horse carrying a man, it flips over to this. And then you can say a dark horse carrying a woman, and it flips over to that one, which is another paraphrase of this, right? You didn't need to talk about the black studded harness, but it doesn't change the performance. And then you can say a woman on the dark horse, and it refers to the woman instead of the horse. So it's relatively sensitive, right? We're doing controlled experiments here. I mean, this is just qualitative, of course, but it's behaving in a way that's reasonable. It doesn't always work this well, but it's happy when it does. Here's some more examples. So here's an image. If we say a giraffe on the left, it picks this guy. If we say a giraffe on the right, it picks this guy. If we have an image, I think this is actually a woman, not a man, but if you say man in red, it locks onto that anyway. And then if you say girl playing tennis, it locks onto this one. So, you know, it's listening properly. What about the speaker? So we can pick a region and we can ask the system to describe the region. So if we ask what's the red box, it will say a cat lying on the left. If it was the blue box, a black cat lying on the right. And that's using a model that does this discriminative training. The baseline model that just does standard LSTM generates ambiguous phrases. So it will say a cat lying on a bed, which is true, but it's ambiguous. Okay, so and here's some more examples. They're a little bit hard to see. But a man wearing a black jacket here and a woman in a black dress there. So that's how these boxes are being described. So you can look at these later. Oh, I should mention, I forgot to mention at the very beginning. So this is a CVPR paper, which actually is going to be presented tomorrow morning. So you're going to hear Junhua Mao, who was our intern, the lead author. He'll give pretty much the same talk tomorrow, so sorry to bore you. I have a few extra added bonus slides at the end just to make it interesting, but and I have a bit more time than he does, so I'm showing more results, but you'll experience deja vu tomorrow morning. Okay, so we had to measure it quantitatively, of course, and we did a variety of experiments where we either used the ground truth region proposal, the ground truth location of the objects, or proposed regions coming from a multi-box model. And then we could either use the human-generated description or the machine-generated description, and then we can measure the precision at one of the true objects, so we're treating it like an object detection problem. We also, so these are all automatic metrics, and the bottom line is basically that the discriminative model that pays attention to ambiguity is about 5% better overall. More interesting perhaps is the human evaluation. So we showed a bunch of generated captions, or region descriptions I should say, and we asked people which one do you prefer, the one from the baseline or the one from the full model, and about 20% of the time they like the full model, and only 15% of the time they like the baseline. So these absolute numbers are quite low, right? It's not doing great, but there's a fairly healthy improvement there. Okay, another thing you can do, which is a cute idea, so we can do semi-supervised training. It's very expensive to collect manually labeled data. So suppose we have some images where we have bounding boxes with captions, and some where we only have bounding boxes but no captions. Well, we can train the model on the data on the left, and then we can apply it to the data on the right, and then just induce the missing labels, bootstrap style, and then train the model on the whole thing. Now, as an extra safety precaution, what Junhua did was to train an ensemble of different models. I'm skipping the details here, but basically to check that it wasn't hallucinating. So we want to be able to filter out imputed annotations that are wrong. So we can check agreement between different models, and if multiple models agree that the annotation has a high score, then we trust it and we add that to the augmented training set. So if we do that, we get a slight improvement over just using the original data. So it was a little disappointing that the gain wasn't bigger, but this is like the last week of his internship, so it could be just lack of tuning. Okay, so the take-home message is to be a better communicator, you need to be a better listener. which is true in life, I think, as well as in machine learning. Now, let's pop back to the original motivating slide. So I said we're trying to do this to help blind people. So what is the connection between what I said and blind users? I can cycle through. Well, basically, there's a fundamental problem, which is I was assuming that someone, the speaker, chose an object of interest and then had to generate a sentence and the listener received it. But who's going to choose which thing to describe, right? There's many things in these cluttered scenes which we're able to detect, but which ones we should actually tell the user depends on the context and their information need. So an alternative, so this is an interesting problem, like an attention model that would know what's important when, and would like just push it to the user without overwhelming them. Another approach is to say, well, let's just ask the user to tell us what they want, right? So there's a nice paper from this paper here, Visual Challenges in the Everyday Lives of Blind People, out of CMU. And they did a user study where they gave blind users cell phones, and they had someone on the other end of the line 24/7 basically, and the blind users could pick up the phone and take a photo and then have an interaction with the human saying, please can you help me do blah. And they logged the data and they did an analysis, what kind of questions the blind users actually want to solve. And they basically fall into these buckets. So there's a lot of questions of the form, you know, they pick up an object and they point it at the camera and they say, what is this? And typically they know like it's a bottle of pills, but they want to know, is it aspirin or Advil or is it whatever, right? So it's fine-grained object recognition. Another very common use case is reading text. So it has a label, or it's a time of day on a clock or a thermometer, and they want to know what it says. They know already it's a thermometer. They want to know what the digits are. Another case which seems rather flippant, but you know, just because you're blind doesn't mean you don't care about how you look. So a lot of people want to match their clothes so they don't look like an idiot walking outside. So they might say, hey, what color is this? Does it go with this? Then of course navigational queries is a big ask. And for outdoor navigation, you know, GPS is pretty good, but not necessarily fine-grained enough. And for indoor navigation, you know, GPS doesn't work. So Google has a system called Tango, which is based on a 3D depth sensor, which you may have heard about. And there's a nice interview with the head of our accessibility team, Eve Anderson, and she talks about using Tango to help blind people do navigation. And another important request is face recognition. So the point about all of this is that these are all important subproblems in the computer vision field already, and they have extremely little overlap with VQA as currently posed. So it feels like the VQA challenge, as in its current form, is fun but not really very relevant. And like if we really want to help users, we might want to have this. I use the term Swiss Army knife. I learned this term from Meg Machado. She invented it, but on the I'm giving a shout out to Microsoft. They have this Seeing AI project that I learned about this morning. And anyway, the idea is you have like a bunch of tools that you can whip out on demand, and the user can tell you which one they're interested in, or maybe the system proactively sends them information. But you can study these more or less in isolation. You might need a contextual model, but you don't necessarily, you don't need to ask, is it going to rain tomorrow? A lot of the questions in the VQA challenge are really not of interest to most users. So I'm going to finish on that provocative note, and I'll take questions.